I'm going to be working the homework solutions for 3.5. This is inverse trig functions. I'm starting with number 1. And it says here for us to find the exact value of arcsine of root 3 over 2. So what this is really asking us is to figure out sine of what angle is root 3 over 2. Well, if we look at the unit circle, we know the common angles and their common values. Sine is always the y-coordinate. So we really want to know when the y-coordinate, at what angle the y-coordinate is root 3 over 2, and that would occur up here and it would occur up here. So the ordered pair there is 1/2 root 3 over 2, and then here this is negative 1/2 root 3 over 2 again. So you can see that the y-coordinates, which is sine of the angle is the y-coordinate, is root 3 over 2 at these two angles. However, because we are working with the arcsine, right, because this is the inverse trig function, we have a domain restriction. Automatically, we cut off the second and third quadrants are not part of our possible solutions. So that means the angle we're looking for must come from the first or the fourth quadrant, and the only angle that would work then is this 60 degrees, or pi over 3. So the answer here is pi over 3. Give me just a second. Whoa. What was that? Was that number 1? I'm sorry, I've just got to get something in order here before I get too far. I forgot my mouse. Must have left it in the office. Oh, how did that happen? Oh, I see what happened. I'm almost done. All right, moving on. Okay, next, part B. Sorry, I didn't see there was 2 parts. That was part A. This is part B. Part B says find arc cosine of -1. And so again, we want to know cosine of what angle is -1. And if we look at our unit circle, cosine is the x-coordinate, and the only place on the unit circle where the x-coordinate is -1 is here at pi. And the domain restriction for the arc cosine is that you must be between 0 and pi, but you can't be past pi. So you can't be in the third or the fourth quadrant. So pi is definitely in there. We're good to go. So the answer here would just be pi. All right, now for number 5. All right, so we want to know where tangent of arctangent of 10, or what, 5a, tangent of arctangent of 10 is. Now the arctan and tangent functions are inverse functions, so they should wipe each other out. The answer should just be 10. I mean, that's what we instinctively think. We just have to make sure there's no restrictions on the domains here. So let's take a look first at the tangent function. if we were to graph tangent, then at pi over 2 and negative pi over 2, we have asymptotes. And then the function repeats itself. Okay, so it's going to repeat itself in both directions. However, when we go and talk about the inverse tangent function, what we do is we just take this one period between negative pi over 2 and pi over 2. So when we graph arctan, this is tangent. Then when we graph arctan, which is its inverse, it's going to look like this. And it will be stuck between pi over 2 and negative pi over 2. So we have horizontal asymptotes instead. So the domain of this tangent function becomes the range of the arctan function. And the range of the tangent function becomes the domain of the arctan. That's the relationship between inverse functions. The domains and ranges switch places. So we just need to make sure that when we evaluate this, that when we're looking at this, that these all make sense. So can we plug the number 10 into arctan? Yeah, 10's out here somewhere. And we're going to get an output, right? And whatever that output is, right, whatever it is, should correspond to some angle here. Right, because our angles are between negative pi over 2 and that's positive pi over 2. It looks like a negative because of the dash. So it makes sense to plug 10 in to arctan. We'll get some angle here. And then if we take tangent of that angle, we're going to get back to 10. So the answer here should just be 10. No problems. Now 5b is going to be slightly different, all right? We have to pay special attention on 5b, to what's happening. So on b, we get arcsine of sine of 7 pi over 3. Okay. Now, for this one, I'm going to go back to the unit circle. You would think that the answer is just going to be 7 pi over 3 because these two undo each other. But we've got something tricky going on here. So let's just go to 7 pi over 3 first. Let's figure out where that is. So this is pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3 puts us right here. So this is the angle, right? If we go all the way around back to here, that's the angle 7 pi over 3. And sine of that angle is the y-coordinate here, which is root 3 over 2. So we know that this right here is root 3 over 2. And now we want to take arcsine of root 3 over 2. So that is asking us, right, this right here is asking us sine of what angle, that's a question mark, sine of what angle is root 3 over 2? Well, it's not 7 pi over 3 because, remember, with the arcsine, we are only allowed to look, arcsine, not cosine. For arcsine, we are only allowed to look in between the first and fourth quadrant. Specifically, we can only look between negative pi over 2 and pi over 2. We've got to look inside that interval. And this angle, 7 pi over 3, you would have to go outside of the first quadrant, come back all the way around and through. So that angle, 7 pi over 3, is outside of this interval. So instead, we just look at this angle here in the first quadrant. What angle is between these two that corresponds to that point? And we looked at that earlier. That's just pi over 3, 60 degrees again. So the answer for that one is pi over 3. A little tricky. They don't just kill each other off. You have to pay attention to domains and ranges there. All right, we're going to move on. Let's see, the next problem that we're supposed to look at is number 15. So for number 15, you're asked to prove that the derivative with respect to x of cosecant inverse of x is equal to negative 1 over x square root of the quantity x squared minus 1. All right, we want to prove that this is true. So to prove this, what I'm going to do is what I did in class, is I'm going to start off by just writing out what I know about cosecant, right? Let's just say, let's let y be equal to cosecant x, right? Then at this point right now, we can take the derivative of cosecant, right? We just don't know what the derivative of cosecant inverse is, and that's what we want. So let's try something here. How shall we do this? Let me write something down here. We know that if we write that down, then cosecant inverse of y equals x. That's taking cosecant on both sides. And then when I differentiate this, that's kind of what I'm looking for up there. You know what? I want to try and do this a little bit different. Sorry. This is literally my first day back from a very long winter break, and I haven't prepared at all for these problems. So let me write this down. Y equals cosecant inverse x. That way everything will be in terms of x. We'll be happy. That's what we're looking at. We want to know the derivative of this. So we want y prime, right? That's what we want. Well, I can't take derivative on both sides because I don't know what the derivative of this is. That's the whole question. So what I'm going to do instead is I'm going to take cosecant on both sides. Take cosecant on both sides. And so long as the domain restrictions are met, these two will wipe each other out, and you'll just get the x on the right-hand side. So cosecant of y equals x. So I started out by saying y is cosecant inverse of x, which really means that cosecant of y is x. And the reason we do that is because I know the derivative of cosecant. So now I'm going to use implicit differentiation. I'm going to take the derivative on both sides of the equation with respect to x. So the derivative of the left side, well, you need to know what the derivative of cosecant is. It's negative cosecant, in this case y, times cotangent y. Then that's just the derivative of cosecant of something. Chain rule says now take derivative of what's inside. The derivative of y is not 1. The derivative of y is y prime, or dy dx. All right? You can look at it both ways. That's the derivative of the left side equals, now the derivative of the right side, the derivative of x with respect to x is 1. All right, so just keep in mind that what I did here, I didn't write it down. So I took the derivative with respect to x on the left side, and I took the derivative with respect to x on the right side. That's 1. This is some chain rule, and when you get onto the inside part of the chain rule, derivative of y is actually y prime. You can see there that I have y prime, which is what I'm trying to solve for. So now what I'll do is I will isolate the y prime by dividing these two factors out. So I get 1 over, and then I'm going to have a negative, right? So negative cosecant y cotangent y. And this is my answer, but my answer is in terms of y, not x. I'd like to get my answer in terms of x, because when we've taken derivatives in the past, if your original function has x's in it, then you want your derivative to have x's in it also. And here it doesn't, right? It has y's. So now let's see what we can do to replace some things here. I know just by looking over here at this very important equation right there, that this piece right here is just x. Okay, so that's good, and that actually looks like it's going to match up right there. That's where x comes from. The question is, what is cotangent of y? Well, this is where we use that reference triangle I talk about in class. So I'm going to go to this equation right here, which is the real important one, and I'm going to draw a right triangle. I'm going to let the angle be y, and the reason I'm using y is because this is the argument of a trig function, so that's usually an angle. And then cosecant is x. Look at this x as being x over 1, like a fraction. Now cosecant is the reciprocal of sine, right? Sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. That means that this is your hypotenuse and that's your opposite side. So hypotenuse opposite. So this triangle matches this equation. And now, because I want to know what cotangent is, cotangent of y would be the reciprocal of tangent. Tangent is opposite over adjacent, so cotangent is adjacent over opposite. We need to know what this side is so we can say adjacent over opposite. So adjacent side, well, you have two sides of a right triangle, so you can solve for this side. Just call this side, let's just call it a for adjacent. Then we know that a squared plus 1 squared equals x squared by the Pythagorean identity. And then a squared equals x squared minus 1, just moving that over, and of course 1 squared is just 1. And then a would be the square root of x squared minus 1, plus or minus, but because a is the length of a side of a triangle, we'll take the positive one. So this right here is going to be replaced with square root of x squared minus 1, and that together should show exactly what we wanted to show, that this would be negative x root x squared minus 1. And the negative down here can go out front or it can go on top, but it's the same thing. So we have shown what we were trying to show. All right. Next thing. How's my battery here? Good. Ooh, got a ways to go here. Okay, find the derivative of the function, simplify where possible. Number 16, you have y is equal to arctangent of x squared. All right, so we need to use some chain rule here because we have composition. We have x squared is inside the arctangent function. So the derivative of this should be, first of all, what is the derivative of arctangent of something? Well, according to the formulas, it's 1 over 1 plus that something squared. So it's going to look like this. 1 over 1 plus whatever was here, the argument, squared. That's a really important derivative to remember. And then chain rule says now multiply by, you've already taken care of this, the derivative of what was in there, which is just 2x. So you get on the top 2x, just slide that up on top, 1 plus x squared, squared is x to the 4th. So that's it there. Let's do number 17 right here. All right, how about y is equal to parentheses arctangent of x squared. So the difference between these two problems is that here the squaring is happening on the entire arctangent function. Here the squaring is only on this x. So it's a little different when we do our chain rule. The outer function here is the squaring, the inner function is the arctangent. So when we take our derivative, we first say, okay, what's the derivative of something squared? Well, that would be 2 times that something. Then you subtract 1 from here, get 1. You don't need to put it, but I just threw it there. So arctan x goes there. And that would take care of the derivative of the outer function. Now take derivative of the inner function and multiply it. So derivative of arctangent of x, well, that's the formula from this section, 1 over 1 plus x squared. And not a lot you can do to clean up. This 2 times this can slide up on top. So you can get something like y prime equals 2 arctangent of x over, and then this denominator 1 plus x squared. All right, let's look at 18. For 18, g of x equals square root of x squared minus 1 times secant inverse of x. So that's multiplication in there. And when we look to take derivative of this, we notice this is going to be a product rule, right? We have a product happening right here. So the product rule says we're going to take derivative of this, multiply it times this, and then plus the derivative of this times this. So I'm going to write that down. G prime of x should be first the derivative of this. Well, that's going to require some chain rule. You have the square root of something. So derivative of the square root of something should be 1 over 2 square roots of that something. And that's kind of a shortcut. And I know in my Cal 1 classes, I tell them when you take derivative of the square root of something, just remember it's always going to be 1 over 2 times the square root of the something. All right, so that's just something that, there's other ways to get it, but everyone should be able to get to this eventually after you work things out. That's just derivative of the square root of something. Then times chain rule, derivative of what's inside. What's inside is x squared minus 1. The derivative of x squared is 2x. Derivative of negative 1 is 0. So we just get 2x there. So that's a derivative of the first function. Then I say times the second one. Now plus, now the derivative of secant inverse of x. So this is on your formula sheet. It is 1 over x root x squared minus 1. Okay, that's the derivative of secant inverse of x. Then times the first function, which is root x squared minus 1. And now we're just going to do a little cleaning up here. Notice that these roots are the same, so those are going to reduce out to go away, basically, become a 1. Those 2's are gone. And I can clean this up to be, let's see, the only thing left on top there is x secant inverse x. And on the bottom, just the root x squared minus 1. And then plus over here, there's nothing left on top except a 1, so 1 over x. I don't see any need to get a common denominator there. I'm happy with that, so I think I'm just going to leave it like that. And give me a second to check this voicemail here. Okay, my audio's back. I might be taking a few breaks here. I apologize that I don't pause the video, but I can't pause it. I have to stop it, and then it creates more than one video, and it's kind of a pain. All right, where are we? 19. Y equals arcsine of 2x plus 1. All right, so we've got some chain rule. The outer function is the arcsine, but the inner function is 2x plus 1. So we'll start with the outer function. The derivative of arcsine of something. Again, these formulas are in your book, but they're also on your formula sheet. The derivative of arcsine of something is 1 over the square root of 1 minus that something, whatever's in here, the argument, squared. Then the chain rule says, now take derivative of what's inside, which is just 2, and multiply it. So that's it. 1 over square root, 2 over, put the 2 on top. 1 minus, and I think we could just leave it like this, but just to show you you could actually expand that, make that 4x squared plus 4x plus 1, and then you'd have to distribute the negative through, so 2 over, let's see, square root of, well, what would happen here is this would become negative, that would become negative, that would become negative, and the 1 minus 1 would go away, so you just have negative 4x squared minus 4x. And that would be it. Could go a little further, though. You could factor a 4 out of each of these, right? You could say, let's pull a 4 out, like that. And the reason you would do that is because now you could split this up into 2 roots, and the square root of 4 is 2. So this right here would come out as a 2, and then that would cancel out, and you get a 1 over square root negative x squared minus x. That would be the cleanest version, and you wouldn't have seen that had you just left it like this. So just be aware that some algebra would take you from here to here. All right, next one. Be aware of the algebra and be able to do the algebra. All right, arctangent. All right, this one is a mess. 20. Arctangent of x minus the square root of 1 plus x squared. Oh yeah, this is going to be a mess. All right, let's go for it. Sorry, this should be y equals? No, let me see. Yeah, y equals. So equals y. All right, so let's take the derivative. This is going to be chain rule. Derivative of arctangent of something will be 1 over 1 plus this something, that quantity squared. And be careful, you cannot just square each one of these, all right? You have to expand that like a foil. I'm not going to do that yet. Times chain rule, derivative of what's inside. So let's be careful here. It's 2 terms, so I'm going to put parentheses. Derivative of x is 1 minus, this is going to be a chain rule. So derivative of square root of something is 1 over 2 times root of the something. Okay, so that's a derivative of this. Then times derivative of what's inside. Derivative of what's inside is just 2x. And then I can close that off. The 2's will cancel here. So let me see what I've got. I've got y prime equals 1 over 1 plus x minus root 1 plus x squared, that quantity squared, times 1 minus x over root 1 plus x squared. Whew. Like that. All right, well, let's try our best here to see if we can't clean this up. Yeah, I think I see what's going to happen. You're not going to like it. All right, so if I need to combine these together, I think the first thing that I would do is try and put these 2 terms together over one fraction or over one denominator. So I'm going to get a common denominator here, meaning that I'm going to turn this 1 actually into a root 1 plus x squared over a root 1 plus x squared. I know that's kind of sloppy, but I'm just giving you the idea of what I'm doing. Turning that 1 over there into this denominator over itself. And that way they'll have the same denominator, put them together. So I'll have this now. I'll have that y prime equals 1 over 1 plus x minus root 1 plus x squared, that quantity squared. Okay, times, now over here I'm going to have one denominator. The denominator is now just 1 plus x squared. But on top, I actually have 2 terms. I have root 1 plus x squared minus x, which is that minus that. All right, now what's the usefulness of that? Is it even useful? Well, I'm very tempted right now to actually square this. Notice these are very close to one another. This right here looks a lot like this right here, doesn't it? And they're only off by a sign, right? If I factor a negative out of this, then they'll match up exactly. In fact, let me do that. If I do a negative right here, it would change that to negative and that to positive, right? It would go like that. And then that's really just, I'll rewrite the order. I'll just switch the order, x minus root of 1 plus x squared. That's what it would look like. And see what I'm saying is that looks like this. The problem is you can't cancel these because there's a plus 1 there. All right, so what do? Well, we do the only thing we can do really, which is to just wondering if I should expand that. Yeah, let me just expand this, all right? I told you this was going to be ugly. 1 plus, okay, let's expand that and I'll do it over here. I'm doing x minus root 1 plus x squared times itself, x minus root 1 plus x squared. So here times here, that's x squared. Then when we do these middle ones, you're going to get negative 2 roots of 1 plus x squared. And then when I do negative this root times negative same root, it's positive, and then the root and the root together, when you multiply them, the root goes away, so you get 1 plus x squared. And actually, there's something real nice here. This x squared and this x squared go together. They don't cancel. I thought they were. I got ahead of myself. I thought they were going to cancel. Oh, well. Okay. All right, so this is that expanded. Let me put it in here. So this is x squared, and x squared is 2x squared. Minus 2 root of 1 plus x squared, and then plus 1. Okay, so that's this expanded, and then I had that plus 1 out there. Notice the plus 1, and the 1 plus 1 is going to be a 2. So let me do that. I'm actually going to do 1 plus 1 and make it a 2. I think I'll just erase it here and turn that into a 2. Just trying to save myself some time here. And then we still have times x minus root 1 plus x squared over root 1 plus x squared. I think we're getting close to something nice happening here. Let's now multiply this times this. So remember, this is 3 terms. They're in parentheses. So this is going to have to go through to each one here, here, and here. And let's see what happens. All right, we've got this times this would give us, and on the top we have, let's get the top in a second. Okay, this times this would be 2x squared root 1 plus x squared. And then this times this, the negative 2 is there, but the root times itself again goes away, so we'll get 1 plus x squared in parentheses. And then 2 of those would give us plus 2 root 1 plus x squared. And that's what it is. I know it looks bad. And on the top, this times the negative 1, I'm just going to leave it. Negative 1 times, I'm going to leave that as x minus root 1 plus x squared. I could distribute the negative back through, and I'd be back to where I was way long time ago. But I'm just going to leave it for right now. And now let me look at this and see if there's anything I can do. Man, really wanting to, I know this is going to simplify to be something really nice. Whoa. Let me see here. All right, let me try this. This is just bothering me up here, so I think I'll distribute that negative back through. This is just an algebra game at this point. All the calculus has really been done. Just a matter of trying to simplify it algebraically. All right, on the bottom, I want to factor something to try and get a factor I can cancel. So let me see, what do they all have? Can we make them both have something in common? How about this? How about these two together? If I put those two together, I can factor out a square root, actually a 2, square root of 1 plus x squared. And then what I would have left is whatever's in front of this one, right, the x squared I would have still. And then whatever was in front of that one, which would just be a 1. Okay, so that might be a little tricky for you to see. What I did is I took 2x squared root 1 plus x squared, and then I took the last one plus 2 root 1 plus x squared, and I factored out a 2 and then the root. So when I factor that out, I get the 2 root 1 plus x squared, and what I'm left with is just the x squared from that one, and then this was everything I factored out, so plus 1. So these two together become this, and then what I still have here is minus 2 times 1 plus x squared, which is that piece. And then 2x squared, yeah. Gosh, I'm so close to getting something here. Both of those have a 1 plus x squared in common, right? Both of those have a 1 plus x squared. And I feel like I'm missing an x here. No? This is causing me some issues. It's definitely going to cause you issues, I know that. But it's important for you to see the struggle here. I'm missing an x somewhere, and I don't see where. Got the common denominator, multiplied that through. When I did this, I got this times this, this there, this there. That was my common denominator. Rewrote the top, put those two together, 2x squared. I pulled out the 2 in the root, x squared plus 1. Then here I still have that one. I see it. I see it. I see it, I see it, I see it. Okay. It's okay, I think I can save it. It was a mistake I made when I squared this. Okay. Apologies. Hey, it's the first day. Trust me, it's not going to be like this all semester. Okay, take that again. When I squared it, I told you I got this. I'm missing something there. I had x minus root 1 plus x squared times x minus root 1 plus x squared. And then first term I got x squared. And then the next one, this should have been negative 2x root 1 plus x squared. That's because I'm going to get x times negative root 1 plus x squared, and then I get another negative root times x, and you'll get 2 of them, negative 2x of these. So this is the key. I forgot this right there. And then the last piece was plus 1 plus x squared. All right, so that, when you put that together right here, this right here is missing an x. All right, well, part of me wants to go back and redo the whole video on this problem and then put it up, but I'm probably just going to leave it because, yeah. All right, so how does that change things? This should be an x right here. When these two go together, nothing's different, But this part right here, you have an x right there. And now things are going to work because these both have a 1 plus x squared, and you'll see on the next step what's going to happen there. I know this is like the first homework solution video set. You're like, oh gosh, this is going to be a long semester with this guy. But I think we're all allowed to have like a warm-up time, right? Even me? Okay, there's the top. On the bottom, since these both have the 1 plus x squared, I'm going to pull it out with this. So I have 2 root 1 plus x squared. I'm pulling out another, I'll put 1 plus x squared instead of x squared plus 1. And then what's left? Okay, well, I took out this thing, right? So, shoot, man, hold on. Maybe I will redo this. I took out an x squared plus 1. That's what I took out. What was left was this and this. So this right here. And then I took that out, so what's left is minus 2x. Like that. One more thing. I'm going to pull out a 2. Okay? So I'm going to pull this 2 out here, pull the 2 out here, place it out here. And now these two are the same, and they cancel. So what you're left with is 1 over 2 times x squared plus 1. Whew. All right. You get the idea, hopefully, of just how ugly this algebra can be. That problem is exceptionally tricky. It's just a matter of taking your time. All right, hopefully the next ones will go a little nicer. All right, next one. Capital G of x equals root 1 minus x squared times arc cosine, which I'm going to write this way, arc cosine of x. So the derivative of this is going to require a product rule because we have a product right there. And what time is it? 11. Okay, and my time on my camera, 42 minutes already? My goodness. All right, product rule. So derivative of the first one, dead marker. 1 over 2 root x. Or sorry, 1 over 2 root of whatever was there times derivative of what's inside, which is negative 2x, times the second function. So that just this is the first part of the product rule. Derivative of this is all that times that plus derivative of arc cosine of x, negative 1 over square root of 1 minus x squared. That's in your formula sheet. And then times the first function, which is root 1 minus x squared. These cancel. We get this is just minus 1 here. And then over here, the 2's cancel. And we have a negative on top. So negative cosine inverse x over root 1 minus x squared. I'm happy with that. I don't think there's really much more we can do with that. Did I forget the x? I did forget the x. X. Right there. X, arc cosine. All right, number 22, arc sine of root of sine of theta. Capital F of theta is, I'm going to write arc sine this way, of root of sine of theta. So we have composition, but we have 3 functions here. We have sine, which is inside a root, which is inside arc sine. So I'm going to start with the outside. The derivative of this should be, derivative of arc sine of something is 1 over square root of 1 minus whatever was in it, which is this, squared. When you square the square root, it goes away, so you get that. Times, now, the derivative of what was in here, which is the square root of something. So 1 over 2 roots of the something, which is sine theta. And now you've done the square root, so now derivative of sine, which is cosine. And just slide the cosine on top, and I believe we can just leave it like that. There's really nothing you can do on the bottom that I can see that's going to make it that much nicer. Put this 2 out here in front. I'll slap this root here. Like what you could do is you could put these 2 roots together, and basically the sine would multiply times this and times that, but I think we would just be stuck at that point, so I'm just going to leave it like that. Number 23. Moving a little faster here now. Number 23, h of t equals cotangent inverse of t plus cotangent inverse of 1 over t. All right, that's the problem. So the derivative of cotangent inverse is negative 1 over 1 plus x squared. So in this case, we have t. So this is the formula. Derivative of this is 1 over, or negative 1 over 1 plus this squared, so t squared. And I'm just doing derivative of these separately because there's addition between them. Now here, this one's going to be a little bit different. Plus, let's see, derivative cotangent inverse of this would be negative 1 over 1 plus, again, that squared this time, 1 over t, but squared. And then chain rule says derivative of what's inside. The derivative of 1 over t is negative 1 over t squared. And the way I did that is 1 over t is the same as t to the negative 1. And when you take derivative of this, the negative 1 comes out, t to the negative 2, because you subtract 1 from this. And that's the same as negative 1 over t squared when you drop the negative exponent down. So everyone should know that. Everyone should know the derivative of 1 over x or 1 over t is negative 1 over t squared or negative 1 over x squared. All right? All right, what can you do here? Negative 1, that's going to be positive 1, so it changes to positive when I multiply those. I'm actually going to leave this one alone and kind of do some work over here. I have plus 1 over, that's 1 on top. Here I have 1 plus, when I square 1 over t squared, I get 1 over t squared. You square the top and bottom. And then I'm multiplying that over here by 1 over t squared. And so just multiply across the top. This t squared is going to distribute to both of those. So you're going to have over here negative 1 over 1 plus t squared plus, and then the 1 times 1 is 1. And then when you distribute here to here, you get t squared. And when you distribute here to here, you're going to get t squared over t squared. That's just going to be 1, so plus 1. And hey, you have the same denominator, so put them together. And something weird is about to happen. You have negative 1 plus 1, that's 0. 0 over t squared plus 1 is just 0. So the derivative of that function is 0. Interesting. That must mean that it's a constant function. On its domain, when you graph it, it should be a constant function because the derivative is 0. All right, 24. Arc cosine of arc sine of t. Arc cosine of arc sine of t. All right, so composition, you have the outer function is arc cosine, the inner function is arc sine. So starting out with the outer function chain rule, derivative of arc cosine of something is negative 1 over the square root of 1 minus whatever was in here, arc sine of t squared. That's it. There's nothing more you can do with that. Then times derivative of what was inside, derivative of arc sine of t is 1 over square root of 1 minus t squared. And there's not a whole lot that we're going to be able to do with that, so we'll just leave it just like that. And we move on to number 25. arctangent of cosine theta. Arctangent of, yeah, cosine, not cosine inverse. So y prime, we have composition again. Outer function is arctangent. Derivative of arctangent of something is 1 over 1 plus whatever was in it, squared. Times derivative of what's in here, which is derivative of cosine is sine, which is sine theta over 1 plus cosine theta. Now your instinct might be telling you, hey, that's a Pythagorean identity. We could do something with that if it was 1 minus cosine theta, but because it's 1 plus cosine theta, we will just leave it alone. All right, number 26, x times natural log of arctan x. Natural log of arctan of x. This looks like it's going to be messy. And this is number 26. Let me check my phone real quick. I need more coffee. Okay, we've got some interesting things happening here. We have a product rule right here, but when we get to this piece, it's a composition. So let's just take it piece by piece. All right, product rule says that I'm going to take derivative of this times this. Derivative of x is 1, so 1 times natural log of arctan of x is just that. Then plus, now derivative of this times this. Let me go ahead and I'll just slap the x down so I don't forget about it. Right here, derivative of natural log of something is 1 over that something. Formula from Cal 1. Times, now the derivative of the inside of a natural log, which is this, derivative of arctangent of x is 1 over 1 plus x squared. And now I'll just rewrite it. I think I'm happy with it like this. I'm not really wanting to put things together and try and get things to cancel because I don't really see that we can do anything with this. So all I did was put these together, and because it's this times this, I have to put that in parentheses. And then on top 1, 1, and then the x. So that should be good there. And now, number 27. X arc sine x plus 1 minus, okay. Y equals x arc sine x plus root 1 minus x squared. I do have a pretty good feeling that things are going to simplify on this one. All right, so we have addition, so we can do these separately, but this one is a product rule. So the derivative will be derivative of x times this, which is just arc sine x, plus derivative of arc sine x, which is 1 over square root 1 minus x squared, times the first function x, and then plus, here we go, derivative of this is 1 over 2 root 1 minus x squared, because the derivative of the square root of something is 1 over 2 times the square root of this something times the derivative of what's inside, which is negative 2x. All right, these twos cancel. We have arc sine x plus x over root 1 minus x squared, and then check this out. 1 and negative x, that's minus, or I'll say plus negative x over square root of 1 minus x squared. These have the same denominators, so we put them together. X take away x is 0. This whole thing goes to 0, and so your answer is just arcsine x. I think what I'll do on number 28, I'll offer number 28 as a bonus. All right? And that can be turned in, let's see, if this homework assignment is due on Thursday, or whatever day, sorry, I don't want to make this course specific, but whatever day this homework assignment is due, that you should have it done, let's make that due as a bonus. You just come bring it to me in the beginning of class. All right, moving along. 32 and 39 are my only ones left. So 32. Find y prime if arctangent of xy equals 1 plus x squared y. So here we have an equation, and you cannot solve this easily for y. So this is what we call an implicit equation. We cannot solve it explicitly for y, so we use implicit differentiation. So what I'm going to do is I'm going to take the derivative with respect to x on the left side and the derivative with respect to x on the right side. Now the derivative on the left side, we first have to take derivative of arctangent of something, which is 1 over 1 plus that something, which is the argument, xy squared, times, chain rule, derivative of what's inside. That's a product rule. And so I'm going to have multiple terms, so I'll put parentheses. Derivative of the first term, or first factor, which is just derivative of x, which is just 1, times the second one, which is y, plus now derivative of y with respect to x is y prime, and then times x. So that's our product rule on that piece right there. That's the derivative of left side. Equals, now the right side. Derivative of 1 is 0. Fine, done. Plus, product rule again. So derivative of x squared is 2x times y, plus now derivative of y, which is y prime, times the first one, which is x squared. All right, looking good. Now what we need to do is get y prime by itself. So there's y prime, there's y prime. I need to release this y prime from the parentheses, so I need to distribute that big ugly thing through to both of these. So when I take this big ugly thing and I multiply it through here, that's just y. It just becomes a y on top, and then 1 plus, I'm going to put x squared y squared here instead. I'm just squaring each one. I can do that because there's multiplication there. And then I do here to here, and it becomes plus y prime x over 1 plus x squared y squared. And then equals 2xy plus y prime x squared. And my goal now is to get this term and this term together on one side of the equation and everything else to the other side of the equation. So I'm going to leave this one here, I'm going to bring this one over, and I'm going to take that and move it over to this side. And the reason we try and isolate the y prime on one side is so we can factor it out. So I will have y prime x over 1 plus x squared y squared. Then I brought this over, so minus y prime x squared equals this 2xy minus, because I'm bringing this over, it's positive over there, so it's going to be negative on this side, minus y over 1 plus x squared y squared. And then I will factor a y prime out of this. So let me factor a y prime out. That will leave me with the x over 1 plus x squared y squared minus x squared equals 2xy minus y over 1 plus x squared y squared. That was supposed to be y squared right there. Sorry. And now I will divide both sides by this. So y prime equals 2xy minus y over 1 plus x squared y squared. That's just this side. I'm dividing it by that entire thing. X over 1 plus x squared y squared minus x squared. And I'm sure that's not the way that they have the answer in the book. I'm sure that we have to do a little more work on this to make it look like the answer they have. I think what we could try and do here, if we're clever, is multiply the top and bottom by 1 plus x squared y squared. 1 plus x squared y squared. And the reason why we do that is because when we do this and we distribute it, it has to go here and here. When we do it to this one, it's going to cancel, and we'll just have the y. Then we do that to here, it's going to cancel here, we'll just have the x. So it'll make things a lot cleaner. Let's see if that gets us to the answer that they want in the book. Y prime equals, okay, so from here to here, it's just going to be 2xy times 1 plus x squared y squared. That's that to that. And then minus, and then we go here to here, everything cancels except the y on top. So minus y over, then when we go here to here, they cancel except for the x. And then minus x squared, right? X squared times this, so 1 plus x squared y squared. And then maybe what we could do is distribute this through here and here, distribute this here and here, and that would give us some final version of an answer. It's not a complex fraction anymore, so this equals, see, this times this is just 2xy. This times this will be plus 2x cubed y cubed, and then minus y, all over here x, and then distribute here and here, so minus x squared minus x to the 4th y squared. That looks like a good answer right there. Let me see if that matches up what they have. Well, yeah, it's close enough. It's good. I mean, it's right, it's just they have it in a slightly different form. I almost dropped my coffee. All right, one more problem. 39. Related rate problem. A ladder 10 feet long leans against a vertical wall. "10-foot ladder leaning against a vertical wall. If the bottom of the ladder slides away from the base of the wall at a speed of 2 feet per second, so if this point right here is moving in that direction at 2 feet per second, now this is a rate that they're giving us, a speed, which should make you think derivative. How fast is the angle between the ladder and the wall changing? Okay, so the angle between the ladder and the wall, this angle right here, theta, how fast is that changing at exactly the moment that the bottom of the ladder is 6 feet from the base of the wall? So this right now, as this point moves out, this point comes down, and that angle starts to change. They want to know how fast that angle is changing at exactly this instant in time. The instant they're talking about is when it looks like this. Remember, that's 10, and then this side right here is 6, right? That's the instant they're talking about. But in general, I call this my general picture. For those of you who took me for Cal 1, you know what I'm talking about. For those who haven't, I basically always draw two pictures for related rate problems. One that is a picture of things moving in motion, and then the other one is a snapshot at the moment in time, or the instant in time. Then what I like to write down is what we're given and what it is that we want. What we're given is that this point is moving at a certain speed. So that point moving means that this distance, which we can call x, is changing at a rate of 2 feet per second. So I can after labeling that, I can write dx dt is growing at a rate of 2 feet per second. Okay? All right, so I know that x is changing by that much. What I want to know is how fast is the angle changing, right? I want to know the rate at which that angle changes when or at the moment that x is 6 feet. All right. Once you've set up what you're given and what you want, what you need to do is find some equation, any equation that you can come up with, that relates those two quantities together, x and theta. So now I go try and find an equation. So if we look at this, we really just have a right triangle. We know that this side is always 10, always 10. This is x and this is theta. And if we turn it sideways, so maybe it might be a little bit easier to see like that. So all I've done is I've just twisted it this way. Then an equation that relates these together is sine. Sine of this angle is opposite over hypotenuse. So I know that sine of theta is equal to x over 10. Or if you'd like, 1/10 x. And once you have the equation, you differentiate it with respect to time, which I could do right now. I could differentiate with respect to time. However, I want d theta dt, and I realize that if I take the derivative over here on this side with respect to time, I'm going to have some chain rule. I'm going to have to take derivative of sine of theta, which is going to be cosine theta, and then derivative of theta, which is d theta dt, and then derivative on the right would just be 1/10 dx dt. So I can do this. There's no problem. But this problem is in the section for inverse trig functions. So why would they put this here? Well, they want you to realize that when you have that equation right here, since you're trying to find d theta dt, you could just take arcsine on both sides. So if I take arcsine of sine theta and take arcsine of the other side, 1/10 x, sorry, then the left side just becomes theta, and the right side is arcsine of 1/10 x. And now, at this point, if I take that equation, which is equivalent to this equation, and differentiate it with respect to time, look at how easy the derivative is on the left side. This is just d theta dt equals, now that's nice because that's what I wanted. It's already solved for. Now you have to take derivative of arcsine of something. Derivative of arcsine of something is 1 over the square root of 1 minus that something, 1/10 x, squared, times the derivative of what's in here. Now be careful at this part. The derivative of 1/10 x is 1/10, not just 1/10, but dx dt, because it's the derivative of x with respect to time, not the derivative of x with respect to x. So the 1/10 is a constant that comes for the ride. Derivative of x with respect to time is dx dt, so we get that. And now we just plug everything in. So if we plug in, let's see, x we know is 6, that's going to go here, right? And dx dt we know is 2. So this will become 1 over, let's see, 1 minus, plugging in 6 here, we get 6/10, which is really 3/5. Okay, so this is 3/5, and when we square it, we get 9/25 times, let's see, put a 2 here, that's going to be 1/5. And then moving on with this, let me see, make this 1 a 25 over 25, subtract, we get 16 over 25, so 1 over 16 over 25 times a fifth. There's many ways you could do this. How about flipping this fraction over? So this up here becomes 25 over 16 times a fifth, and then 1 and 5, so 5/16. That's what we get. And that is d theta dt. We just need the units now. So d theta dt is 5/16. And now, how do we measure theta in this problem? Well, it's an angle, and we always measure in radians when we're doing related rate problems. So this is going to be radians. I'm just going to put rads per, And then our unit of time is seconds in the problem, so per second. Six tenths. What did I mess up? I messed up something. 25 minus, oh, you know what I forgot? Oh, my goodness. This was square root. Oopsie. And then that's square root. And that makes this, I knew I missed something there. This is 4/5, so this would have been 1 over 4/5 is the same as 5/4. And then that would have been cancel, 1/4. Okay, 1/4 radians. 1/4 of a radian per second. So at that instant that the ladder is 6 feet from the bottom, the angle is changing at 1/4 of a radian per second. Wow, all right, well, that was an hour and 12 minutes, or now 11 minutes or so. All right, I've just got to work the rust off here. I'll get the other sections going later, not today. I think I'm done.